Hello, in this video we're going to look at the Bolzano-Weierstrass theorem, and there's two versions that are commonly given, and we'll review them both. The first one I learned in my topology class, and the second one I learned in more of a real analysis class, but we'll go through them both. First, we need a definition. A number is a limit point or cluster point or accumulation point. All three of those can be interchanged, and it means the same thing. So a number is a limit point of a set A if there's an epsilon greater than 0 such that this interval contains infinitely many points of A. Then that's called a limit point or a cluster point. And the first version of the Bolzano-Weierstrass theorem is every bounded infinite set of real numbers has at least one limit point. Okay. And here's the proof. Since A is bounded, there exists an M such that A is a subset of this interval, minus A to M, right? Because it's a bounded set. So we can find an M, and it may be so big that, but that's all right. There's an M out there. So the length of this is 2M, M minus a minus M is 2M. So now if we divide A into two equal length closed sets, say minus M to 0 and 0 to minus M, one of those or both is an infinite set, right? Because minus M to M was an infinite set, so one of those still has to be infinite. Now let's choose one with the infinite number of points, and we're going to denote it by A1. So A1 is A1 to B1, and it has length of 2M divided by 2. So we just take this divided by 2, and that's the new length of our subinterval. Now let's divide, and we're going to keep doing this process. So now divide A1 into two sets of equal length. Choose the one with an infinite number of points denoted by A2. And since we just halved A1, the length of A2 is going to be 2M over 2 squared. And we divide it by 2 again. Now we're going to continue this for each n. So we're going to create intervals capital AN, which are equal to AN to BN. And each one of those contains infinitely many points, and their length is 2M divided by 2 raised to the nth power. So note that each time we're creating those intervals, we're taking, we're dividing it into two equal length. So each interval is now a subset of the previous one. So we're creating these nested intervals, and this is for all n. And note that the length of those intervals will eventually get to 0, because if we're halving it each time, the length is 2M over 2n squared, or 2 to the nth power. And so if we let n go to infinity, the length of those intervals go to 0. And so by the nested intervals theorem, which we covered in monotone sequences of real numbers, the infinite intersection of all those intervals contains 1 point, and 1 point exactly. And so note that P is an element of every single one of those intervals. So let's let epsilon be greater than 0. Then there exists an n that the length of the subinterval, we can just keep raising 2 to the nth power bigger and bigger and bigger until this gets so incredibly small, it's smaller than epsilon, right? And that's for any epsilon greater than 0 that we choose. We can find a number, make this smaller. So thus, the subinterval A capital N is, it's a subset of this, right? Because the length of this is 2 to the n, and and P is the center, the only point in all the intersections. So if we go back out If we go backwards, then that is this. But this interval is actually a subset of this interval, right? Because we've created an n. This is smaller than epsilon, so this is contained in here. Now, which shows that this interval, p minus epsilon to p plus epsilon, contains infinitely many points of A. So therefore, p is a limit point. Remember, each subinterval had an infinite number of points. So this has an infinite number of points, and which is contained in this interval. So therefore, by definition, it's a limit point. Now, the second version of the Bolzano-Weierstrass theorem is this. Every bounded sequence of real numbers has a convergent subsequence. And so both of those, they're interchangeable, and you can prove one, implies the other and vice versa. So let AN be a bounded sequence, two cases. AN has an infinite number of terms with the same value. Let these terms be a subsequence, and clearly they converge because they all have the same value. So that's a kind of a trivial case with this convergence. So it has a convergent subsequence. So case 2, let's say that AN has infinitely many distinct values. And by the Bolzano-Weierstrass theorem part 1, AN has a limit point, right? It's a bounded infinite set. So it has a limit point. And that means there's an epsilon greater than 0 such that this interval contains an infinitely many terms of AN. Now, by theorem 2 of a video, subsequences of real numbers, there exists a subsequence of AN that converges to P. And therefore, we've proved the theorem. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.